Transformer inrush currents can indeed appear to the right of a circuit breaker's time current characteristic, or TCC, curve. This placement indicates a potential for the circuit breaker to trip during the transformer's inrush period. However, it is not a certainty that the breaker will trip every time. Several factors determine whether a circuit breaker will trip in response to transformer inrush current. Firstly, the duration of the inrush current is crucial. Transformer inrush is a transient phenomenon, meaning it occurs for a relatively short period, typically a few cycles of the alternating current waveform. If the duration of the inrush current is short enough, the circuit breaker's thermal inertia might prevent it from reaching its tripping threshold. The TCC curve illustrates the time it takes for the breaker to trip at different current levels. If the inrush current decays quickly, the breaker may not have enough time to heat up and initiate a trip. Secondly, the interrupting rating of the circuit breaker plays a vital role. The interrupting rating signifies the maximum fault current the breaker can safely interrupt without sustaining damage. This rating is different from the continuous current rating, which indicates the steady state current the breaker can carry without tripping. If the transformer inrush current exceeds the breaker's interrupting rating, the breaker may trip regardless of the duration. However, even if the inrush current is below the interrupting rating, the breaker can still trip if the current persists for too long, as dictated by the TCC curve. Thirdly, the type of circuit breaker influences its response to inrush currents. Different breaker types have varying TCC curves and operating characteristics. For example, inverse time circuit breakers are designed to trip faster at higher currents. Some circuit breakers are specifically designed to handle inrush currents without tripping, often labeled as high magnetic or instantaneous trip breakers. These breakers allow for a short duration of a current, such as transformer inrush, without initiating a trip. These breakers typically have a higher instantaneous trip setting. Fourthly, the transformer's design and size affect the magnitude and duration of the inrush current. Larger transformers generally exhibit higher inrush currents than smaller ones. The core material and construction also play a role. Transformers with grain-oriented silicon steel cores tend to have lower inrush currents than those with other core materials. Fifthly, the system impedance affects the inrush current. Higher system impedance limits the magnitude of the inrush current, reducing the likelihood of a breaker trip. The impedance includes the transformer's impedance, the source impedance, and the impedance of the connecting conductors. To mitigate nuisance tripping due to transformer inrush, several strategies can be employed. Firstly, use circuit breakers with appropriate TCC curves. Select breakers with time delay characteristics that allow for short duration overcurrents without tripping. Inverse time breakers are often suitable for transformer protection because they provide overload protection while tolerating inrush currents. Secondly, increase the circuit breaker's interrupting rating. Choose a breaker with an interrupting rating that exceeds the maximum expected inrush current. This provides a safety margin and reduces the risk of damage to the breaker during an inrush event. Thirdly, utilize inrush current limiting devices. These devices reduce the magnitude of the inrush current, preventing it from exceeding the breaker's tripping threshold. Inrush current limiters can be installed in series with the transformer to dampen the inrush current. These can be resistors, reactors, or solid-state devices. Fourthly, employ controlled switching techniques. Controlled switching involves energizing the transformer at a specific point in the voltage waveform to minimize the inrush current. This technique requires specialized switching devices and control systems. Fifthly, specify transformers with lower inrush current characteristics. When purchasing new transformers, consider specifying models with grain-oriented silicon steel cores or other features that reduce inrush currents. Sixthly, consider using a soft starter. Soft starters can gradually increase the voltage applied to the transformer, limiting the inrush current during energization. These are more commonly used for motor starting, but can be adapted for transformer applications in some cases. Seventhly, implement proper coordination studies. Coordination studies involve analyzing the TCC codes of all protective devices and electrical system to ensure that they operate in a coordinated manner. This helps to prevent nuisance tripping and ensure that the appropriate breaker trips during a fault. In summary, the fact that a transformer inrush current curve lies to the right of a circuit breaker's TCC curve does not automatically guarantee a trip. The actual outcome depends on a combination of factors, including the duration of the inrush current, the breaker's interrupting rating, the breaker's type and TCC curve, the transformer's design, and the system impedance. By carefully considering these factors and implementing appropriate mitigation strategies, nuisance tripping due to transformer inrush can be minimized. Now let's talk about applying specific numbers and NEC, National Electrical Code, requirements to this topic. For example, let's say we have a 75 kV ampere transformer with a 480 volts primary and a 208 volts secondary. The transformer impedance is 5%. We can calculate the full load current on both the primary and secondary sides. The primary full load current is calculated as 75,000 volt amperes divided by 480 volts, which equals 156.25 amps. The secondary full load current is calculated as 75,000 volt amperes divided by 208 volts, which equals 360.58 amps. The inrush current can be estimated as 8 to 12 times the full load current. So, on the primary side, the inrush current could be between 1250 amps and 1875 amps. On the secondary side, the inrush current could be between 2885 amps and 4327 amps. The circuit breaker protecting the primary side must have an interrupting rating greater than the available fault current at the transformer primary terminals. To determine this, we need to know the upstream source impedance. Let's assume the upstream impedance results in a fault current of 10,000 amps at the primary terminals. Therefore, the primary breaker should have an interrupting rating of at least 10,000 amps. Now, the NEC provides guidelines for overcurrent protection of transformers in Article 450. 3. For transformers rated over 600 volts, the primary overcurrent protection shall be provided in accordance with Table 450. 3a. For transformers rated 600 volts or less, the primary overcurrent protection shall be provided in accordance with Table 450. 3b. These tables specify the maximum allowable overcurrent protection based on the transformer's rated current. For example, Table 450. 3b allows for primary overcurrent protection device rated at up to 125% of the transformer's rated primary current if the primary current is less than 9 amps. If the primary current is 9 amps or more, the overcurrent device can be rated up to 250% of the rated primary current if a circuit breaker is used. For our 75 kV ampere transformer with a primary current of 156.25 amps, we can use a circuit breaker rated at up to 250% of 156.25 amps. That gives us 390.625 amps. So, a 400 amp circuit breaker would be acceptable. However, we must also consider the transformer's inrush current. If the 400 amps breaker trips during inrush, we would need to use a larger breaker or implement inrush current limiting techniques. One option is to use a breaker with an instantaneous trip setting that is above the inrush current. For example, if the inrush current is 1875 amps, we could use a breaker with an instantaneous trip setting of 2000 amps. This would allow the inrush current to pass without tripping the breaker, but it would still provide protection against sustained overloads and faults. On the secondary side, the overcurrent protection requirements are similar. According to the NEC, the secondary overcurrent protection shall be sized no higher than 125% of the transformer's rated secondary current. For our 75 kV ampere transformer with a secondary current of 360.58 amps, we can use a circuit breaker rated at up to 125% to 360.58 amps, which is 450.73 amps. So, a 450 amps or 500 amp circuit breaker would be acceptable. Again, we must consider the inrush current. If the 450 amps or 500 amps breaker trips during inrush, we would need to use a larger breaker or implement inrush current limiting techniques. Remember that these are just examples. Specific overcurrent protection requirements for a transformer will depend on its size, voltage, impedance, and the specific application. Always consult the NEC and other applicable codes and standards to ensure that the transformer is properly protected. Also, coordination studies are critical to ensure the breakers operate properly in relation to one another under fault conditions. In addition to circuit breakers, fuses can also be used for transformer protection. Fuses have different characteristics than circuit breakers. Fuses generally have a faster response time and a higher interrupting rating than circuit breakers of similar size. However, fuses must be replaced after they blow, while circuit breakers can be reset. The choice between using a circuit breaker or a fuse for transformer protection depends on various factors, including the application, the available fault current, and the desired level of protection. Some applications may require both a circuit breaker and a fuse for optimal protection. For example, a circuit breaker may be used to protect against overloads, while a fuse may be used to protect against high fault currents. In summary, selecting the appropriate overcurrent protection for a transformer involves careful consideration of the transformer's characteristics, the system impedance, the available fault current, and the applicable codes and standards. Inrush current is a critical factor that must be considered to prevent nuisance tripping. Proper coordination studies are essential to ensure that the protective devices operate in a coordinated manner. A qualified electrical engineer should perform these calculations and select the appropriate protective devices. Let's consider the effect of transformer impedance on inrush current. Transformers have an impedance typically expressed as a percentage, which limits the fault current and, to some extent, the inrush current. A lower impedance transformer will generally have a higher inrush current than a higher impedance transformer of the same kilovolt-ampere rating. This is because a lower impedance allows for a higher current flow during the initial energization. The transformer impedance also affects the voltage regulation of the transformer. Lower impedance transformers tend to have better voltage regulation, meaning that the output voltage remains more stable under varying load conditions. However, lower impedance transformers also require larger overcurrent protection devices to accommodate the higher inrush currents. Higher impedance transformers have higher voltage drops and larger voltage fluctuations under varying load conditions but lower inrush currents. The selection of the transformer impedance is a trade-off between voltage regulation and inrush current. The selection depends on the specific application and the requirements of the electrical system. In some cases, it may be necessary to specify a transformer with a specific impedance to meet the system requirements. Another important consideration is the transformer's core material. The core material affects the transformer's efficiency, inrush current, and harmonic content. Transformers with grain-oriented silicon steel cores tend to have lower losses, lower inrush currents, and lower harmonic distortion than transformers with other core materials. Grain-oriented silicon steel cores are more expensive than other core materials, but they can provide significant benefits in terms of efficiency and performance. Transformers with amorphous metal cores have even lower losses than transformers with grain-oriented silicon steel cores. However, amorphous metal cores are more expensive and more difficult to manufacture. The choice of core material depends on the specific application and the cost-benefit analysis. The harmonic content of the inrush current can also be a concern. Inrush currents can contain significant harmonic components which can cause problems with other equipment connected to the electrical system. Harmonic filters may be required to mitigate the effects of harmonic currents. Now let's delve into the practical steps of selecting a circuit breaker for transformer protection, keeping in mind the inrush current considerations. Firstly, determine the transformer's full load current, both in the primary and secondary sides, using the kilovolt-ampere rating and voltage. Secondly, estimate the inrush current, typically 8 to 12 times the full load current. Consult the transformer manufacturer's data sheets for more accurate inrush current values if available. Thirdly, determine the available fault current at the transformer's terminals. This requires a fault current study or analysis of the upstream impedance. Fourthly, select a circuit breaker with an interrupting rating greater than the available fault current. This ensures that the breaker can safely interrupt a fault without damage. Fifthly, choose a circuit breaker with a TCC curve that allows for the inrush current without tripping. This may require using a breaker with a time delay characteristic or an instantaneous strip setting above the inrush current. Sixthly, verify that the selected circuit breaker meets the requirements of the NEC and other applicable codes and standards. Seventhly, perform a coordination study to ensure that the circuit breaker operates in a coordinated manner with other protective devices in the electrical system. Eighthly, consider using inrush current limiting devices if the inrush current is excessively high or if nuisance tripping is a concern. Ninthly, document all calculations and assumptions used in the selection process. This provides a record of the decision-making process and facilitates future troubleshooting. Tenthly, have a qualified electrical engineer review and approve the circuit breaker selection. This ensures that the selection is correct and meets all applicable requirements. Finally, it's important to periodically review the circuit breaker selection and coordination studies to ensure that they remain valid. Changes in the electrical system, such as the addition of new loads or equipment, can affect the fault current and inrush current, and may require adjustments to the overcurrent protection. Regular maintenance and testing of circuit breakers are also essential to ensure their proper operation and reliability. This includes visual inspections, insulation resistance tests, and contact resistance tests. These tests can help identify potential problems before they lead to failures. In addition to the NEC, other standards may apply to the selection and application of circuit breakers for transformer protection. These standards may include Institute of Electrical and Electronics Engineers, or IEE, standards, American National Standards Institute, or ANSI, standards, and National Electrical Manufacturers Association, or NEMA, standards. It's important to be familiar with these standards and to comply with their requirements. For example, IEE Standard 242, commonly known as the Buff Book, provides guidance on the protection and coordination of industrial and commercial power systems. This standard includes information on transformer protection and circuit breaker selection. Similarly, ANSI Standard C37 13 covers the requirements for low-voltage alternating current power circuit breakers used in enclosed assemblies. This standard includes information on interrupting ratings, trip characteristics, and testing requirements. NEMA standards provide guidance on the construction, performance, and testing of electrical equipment, including circuit breakers. By following these standards, electrical engineers can ensure that circuit breakers are selected and applied correctly, providing reliable protection for transformers and other electrical equipment. The considerations discussed highlight the complexity of transformer protection and the importance of careful analysis and design. It's not simply a matter of choosing a circuit breaker based on the transformer's full load current. Inrush current, fault current coordination, and applicable standards must all be taken into account. A thorough understanding of these factors is essential for ensuring the safe and reliable operation of electrical systems.